You ever see an AI recognize a face in a crowd or generate some incredible art and just wonder, how on earth did it learn to do that? It feels like magic, but it's not. It's a methodical process, a pipeline. And today, we're going to tear that whole thing down and see exactly how it works, from the very first guess to a full-blown state-of-the-art model. All right, so first things first, let's talk about the heart of the machine, the AI's learning engine. This is the core idea that lets pretty much any modern AI, whether it's a chatbot or an image generator, get better over time. And that engine has a name, backpropagation. It really is the learning engine behind modern deep learning. Here's the gist. When a model gets something wrong, backpropagation is the process that goes all the way back through the network to figure out which connections, think of them like thousands of tiny little knobs, were most responsible for the mistake. It then tells the AI exactly which knobs to turn and in which direction to do a little bit better next time. So here's the game plan for this explainer. We've just met the learning engine. Next, we'll walk through the four-step training loop that it powers. Then we'll get into choosing something called an optimizer and watch a showdown between two of the big ones. After that, we'll uncover a really clever fix for the underdog and wrap up with why all these little details matter a lot. Okay, so let's get into the main process. You gotta understand, an AI doesn't just learn everything in one big aha moment. Nope. It learns through a constant, super fast cycle of tiny adjustments. And that cycle is what we call the four-step training loop. You can kind of think of it like a little four-step dance. Step 1, forward propagation. The model gets an input, let's say a photo of a dog, and it makes the guess. I'm pretty sure that's a cat. Step 2, loss computation. It gets compared to the right answer, dog, and gets a wrongness score. We call it a loss. The more wrong it is, the higher that score. Step 3 is backpropagation, our learning engine. It takes that score and traces it backwards, assigning a little piece of the blame to every single knob that led to that bad guess. And finally, step 4, the parameter update. An optimizer uses all that blame information to go and tweak every single one of those knobs or parameters just a tiny bit. The goal is to make it just a little less likely to say cat the next time it sees a dog. Now imagine this dance repeating millions, even billions of times. Let's zoom in on that final, crucial fourth step, the update. This isn't just a random tweak. It's guided by a specific algorithm we call an optimizer. The optimizer is like the driver. It takes the directions from backpropagation and decides exactly how to turn all those knobs. And let me tell you, the kind of driver you choose makes a huge difference. Now, two of the most common drivers you'll run into are SGD and AtomW. On one hand, you have SGD. It's the classic, the old reliable. It's been around forever, it works, and it's pretty light on memory, using about 8 to 12 bytes for every single parameter in the model. Then you've got AtomW. It's the more modern, sophisticated option. Its killer feature is that it's adaptive. This means it can change the learning speed for each knob individually. So while SGD uses one speed for the whole network, AtomW can make huge adjustments over here and tiny, careful ones over there, all in the same step. But that extra intelligence costs you. It uses more memory, around 16 bytes per parameter. For a long time, the choice between these two wasn't a huge deal. They often performed about the same. But then, new kinds of models came along, these powerful things called vision transformers. And suddenly, in this modern optimizer showdown, one of them started pulling way ahead. And here's the data to prove it. What you're looking at are the results from training a vision transformer on a new task. And look at the accuracy on data it's never seen before, what we call out of distribution. AtomW is a full 8.1% better than SGD. In the world of AI, an 8.1% gap isn't just a gap, it's a canyon. It's a massive difference, right? An 8% advantage is the kind of thing that makes everyone in the field stop and ask, whoa, what is going on here? So that's the big question. Why? Why is the classic, reliable SGD suddenly falling apart on these new models? What is AtomW doing that's so special? And this chart, this is the smoking gun. It shows us the strength of the update signal, what we call gradients, for the different layers in the network. The black circles are most of the layers, pretty normal. But look at those red squares. That's the very first layer of the network. On these vision transformers, that first layer's update signal is a massive outlier. It's basically screaming for a change compared to all the other layers. Now, SGD hears that scream, and since it treats every layer the same, it massively overcorrects, totally messing up that important first layer. But AtomW, because it's adaptive, it can see that one screaming layer and essentially say, okay, you calm down a bit, and apply a much smarter, more balanced update across the board. So, case closed, right?
Atom W is just better for these new models, end of story. Well, not so fast. This is where things get really interesting. Because the researchers didn't just find the problem, they also found a shockingly simple fix to bring good old SGD back into the game.
And the solution is, well, it's so simple, it's beautiful. If that one layer is causing all the trouble because its update signal is too loud, what if you just tell it to be quiet? What if you just freeze it? Tell it not to update at all? And here is the result. On the left, you see the technique. We just lock the weights in that first embedding layer and don't let them change. That's literally it. And on the right, would you look at that? The performance of SGD with this freeze embed trick just snaps right back up. That 8.1% gap in accuracy, gone. Boof! Completely vanished. With one tiny change, SGD is performing just as well as the much more complex Atom W. It's incredible. And this isn't just some neat academic trick. This has huge, real-world consequences. Remember how Atomway uses more memory? Well, it turns out it uses 36% more GPU memory than this fixed version of SGD. 36%. That is a massive amount of memory savings. That can be the difference between being able to train a giant model or not, or being able to do it on cheaper hardware. It basically makes cutting-edge AI more accessible for everyone. Which brings us to our big finish. Why the details matter. This whole story, from a performance mystery to digging into the guts of the model and finding a simple, elegant fix, is a perfect example of how we make progress in AI. It's not always about inventing some brand new, crazy thing. Sometimes it's about deeply understanding the tools we already have and figuring out their quirks. So let's just quickly recap the big takeaways here. First, that four-step dance: forward pass, loss, backpropagation, update. That's the core of everything. Second, your choice of optimizer, like SGD or Atom W, is a really big deal, especially for new models like Vision Transformers. We saw how Atom W's ability to adapt gives it a huge advantage with those weird outlier gradients. But we also learned that a super simple freeze embed trick makes SGD just as good, while saving a ton of memory. And really, the biggest lesson of all is that taking the time to understand why something is broken is the fastest path to a real practical innovation. And that just leaves us with this one last fascinating question to chew on. Think about it. The key to getting a state-of-the-art result was a totally counterintuitive move, telling a part of the AI not to learn. If that's possible, it just makes you wonder, what other fundamental rules of how we train these things are really just assumptions, waiting for someone to come along and break them?